Welcome to this series on neural network programming with PyTorch. It's time now to learn about the weight tensors inside our CNN. We'll find that these weight tensors live inside our layers and are the learnable parameters of our network. Without further ado, let's get started. In the last couple of posts in this series, we started building our CNN and we put in some work to understand the layers we defined inside our network's constructor. Ultimately, our next step in the overall process is to use these layers inside our for method. But right now, let's take a look at the learnable parameters of our network. We already know about hyperparameters. We saw that hyperparameters are parameters whose values are picked arbitrarily. The hyperparameters we've used up to this point were hyperparameters that we use to construct our network's architecture through the layers we constructed and assigned as class attributes. These hyperparameters aren't the only hyperparameters though. We'll see more hyperparameters for sure when we start the training process. What we're concerned with now, though, is a different type of parameter called a learnable parameter.
Learnable parameters are parameters whose values are learned during the training process. With learnable parameters, we typically start out with a set of arbitrary values, and these values then get updated in an iterative fashion as the network learns. In fact, when we say that a network is learning, we specifically mean that the network is learning the appropriate values for the learnable parameters. Appropriate values are values that minimize the loss function.
When it comes to our network, we might be thinking, well, where are these learnable parameters? All we have so far is a network class with layers that have been assigned as class attributes. Well, the learnable parameters are the weights inside our network, and they live inside each layer. Using PyTorch, we can inspect the weights directly. So let's grab an instance of our network class and see this. Remember, to get an object instance of our network class, we type the class name followed by parentheses. When this code executes, the code inside the init class constructor will run, assigning our layers as class attributes and then returning the object instance. The name init is short for initialize. In an object's case, the attributes are initialized with values, and these values can indeed be other objects. In this way, objects can be nested inside other objects. This is the case with our network class, whose class attributes are initialized with instances of PyTorch layer classes. After the object is initialized, we can then access our object using the network variable. Okay, so before we start to work with our newly created network object, have a look at what happens when we pass our network to Python's print function. The print function prints to the console a string representation of our network. With a sharp eye, we can notice that the printed output here is detailing our network's architecture, listing out our network's layers, and showing the values that were passed to the layer constructors. One question is though, how exactly is this happening? Where is this string representation coming from? Well, our network class is inheriting this functionality from the PyTorch module base class. Watch what happens if we stop extending the neural network module class. Now we don't get the nice descriptive output like before. Instead, we get this technical gibberish, which is the default Python string representation that we get if we don't explicitly provide one. For this reason, in object-oriented programming, we usually want to provide a string representation of our object inside our classes so that we get useful information about the object when it gets printed. This string representation comes from Python's default base class called object. All Python classes automatically extend the object class. If we want to provide a custom string representation for our object, we can do it, but we need to introduce another object-oriented concept called overriding.
When we extend a class, we get all of its functionality. And to complement this, we can add additional functionality. However, we can do more. We can also override existing functionality by changing it to behave differently.
We can override Python's default string representation using the _repr__ function. This name is short for representation. This time, when we pass the network to the print function, the string that we specified in our class definition is printed in place of Python's default string. This is overriding in action. When we talked about OOP before, we learned about the $init_" method and how it is a special Python method for constructing objects. Well, there are other special methods like this that we'll definitely encounter, and _repr_ is one of them. All the special OOP methods in Python typically have the _ pre and postfixes. This is how we can distinguish them as being special. In PyTorch's case, this is how the PyTorch module base class works as well. The module base class overrides the repr function. And if we look in the PyTorch source code in the module class, we indeed see this. So let's take a look at this string representation. What's actually here? For the most part, the string representation that PyTorch gives us pretty much matches what we would expect based on how we configured our network's layers. For the convolutional layers, the kernel size argument is a Python tuple 5,5, even though we only pass the number 5 in the constructor. This is because our filters actually have a height and width. And when we pass a single number to the constructor, the code inside the layers constructor assumes that we want a square filter. Next, we have the stride, which is an additional parameter that we could have set, but we left it out. And when the stride is not specified in the layer constructor, the layer automatically sets it.
The stride tells the conv layer how far the filter should slide after each operation in the overall convolution. This tuple says to slide down by 1 unit when moving to the right, and also by 1 unit when moving down.
For the linear layers, we have an additional parameter called bias, which has a default parameter value of true, and it can be turned off by setting it to false. One thing to note about the information displayed for our objects when we print them is that it's completely arbitrary information. As developers, we can decide to put any information there. However, the Python documentation tells us that the info should be complete enough that it can be used to reconstruct the object if needed. So that's what we want to shoot for when building our own classes. Now that we've got an instance of our network and we've reviewed our layers, let's see how we can access them in code. In Python and many other programming languages, we access attributes and methods of objects using dot notation. This is dot notation in action. With dot notation, we use a dot to indicate that we want to sort of open up the object and access something that's inside. We've already been using this quite a bit, so the mention here just gives us a label for the concept. Something to notice about this that pertains directly to what we were just talking about with the string representation is that each of these pieces of code are also giving us a string representation of each layer. In the network's case, the network class is really just compiling all of this data together to give us a single output for the network. Now that we have access to each of our layers, we can access the weights inside each layer. Let's see this for our first convolutional layer. The output here is a tensor, but before we look at this tensor, let's talk OOP for a moment. This is a good example that showcases how objects are nested. We first access the conf layer object that lives inside the network object. Then we access the weight tensor object that lives inside the conf layer object. So all of these objects are chained or linked together. One thing to notice about this output is that it says parameter containing at the top. This is because this particular tensor is a special tensor because its values or scalar components are indeed learnable parameters of our network. This means that the values inside this tensor, the ones we see here, are actually learned as the network is trained. As we train, these weight values are updated in such a way that the loss function is minimized. To keep track of all the weight tensors inside the network, PyTorch has a special class called parameter. The parameter class extends the tensor class, and so the weight tensor inside every layer is an instance of this parameter class. This is why we saw the parameter containing text at the top of the tensor output. Looking here in the PyTorch source code, we can see that the parameter class is overriding the dunder repr method by prepending this string to the result of the tensor class's string representation. If we are extending a class, we can access its methods using the super keyword, and that's what's happening here. The way this parameter class comes into play with PyTorch is that the neural network module class is basically looking for any attributes of a module whose values are instances of the parameter class. And when it finds an instance of the parameter class, it keeps track of it. All of this so far is really just PyTorch technical details that go on behind the scenes. We'll see this come into play in a bit. For our understanding now though, the important part is the interpretation of the shape of the weight tensors. This is where we'll start to use the knowledge we learned about tensors early on in the series. Let's look at the shapes now, and then we'll interpret them. In the last post, we said that the parameter values we pass to our layers directly impact our network's weights. This is where we'll see this impact. For convolutional layers, the weight values live inside the filters, and in code, the filters are actually the weight tensors themselves. The convolution operation inside a layer is an operation between the input channels to the layer and the filter inside the layer. This means that what we really have is an operation between two tensors. With that being said, let's interpret these weight tensors, which will allow us to better understand the convolution operations inside our network. Remember, the shape of a tensor really encodes all of the information we need to know about the tensor. For our first conv layer, we have one color channel that should be convolved by 6 filters of size 5 by 5 to produce 6 output channels. This is how we interpret the values inside our layer constructor. We did this last time. Inside our layer though, we don't explicitly have 6 weight tensors for each of the 6 filters. We actually represent all 6 filters using a single weight tensor whose shape reflects or accounts for the 6 filters. The shape of the weight tensor for the first convolutional layer shows us that we have a rank 4 weight tensor. The first axis has a length of 6, and this is where we account for the 6 filters. The second axis has a length of 1, which accounts for the single input channel, and the last 2 axes account for the height and width of each filter. The way to think about this is as if we are sort of packaging all of our filters into a single tensor. Now, the second conv layer has 12 filters, and instead of convolving a single input channel, there are 6 input channels coming from the previous layer. Think of this value of 6 here as giving each of the filters some depth. Instead of having a single filter that convolves all the channels iteratively, our filter has a depth that matches the number of channels. And so it's able to slide across all of the channels in one go. The 2 main takeaways about these weights for these conv layers is that our filters are represented using a single tensor, and each filter inside the tensor also has a depth that accounts for the input channels that are being convolved. So to summarize, our tensors are rank 4 tensors. The first axis represents the number of filters. The second axis represents the depth of each filter, which corresponds to the number of input channels being convolved. And the last two axes represent the height and width of each filter. We can pull any single filter out by indexing into the weight tensor's first axis. This gives us a single filter that has a height and width of 5 and a depth of 6. Let's shift gears now and look at the weight tensors for linear layers. With linear layers or fully connected layers, we have flattened rank 1 tensors as input and as output. The way we transform the in features to the out features in a linear layer is by using a rank 2 tensor that is commonly called a weight matrix. This is due to the fact that the weight tensor is of rank 2 with height and width axes. Here we can see that each of our linear layers have a rank 2 tensor as the weight tensor. The pattern that we can see here is that the height has a length that is equal to the desired output features, and the width has the length of the input features. This fact is due to how matrix multiplication is performed. Let's see this in action with a smaller example. Suppose we have two rank 2 tensors. The first has a shape of 3 by 4, and the second has a shape of 4 by 1. Since we are demonstrating something called matrix multiplication, we'll note that both of these rank 2 tensors are indeed matrices. With this setup, matrix multiplication works like this. For each row-column combination in the output, the value is obtained by taking the dot product of the corresponding row of the first matrix with the corresponding column of the second matrix. Since the second matrix in our example only has one column, we will use it all 3 times. But this idea does generalize. The rule for this operation to work is that the number of columns in the first matrix must match the number of rows in the second matrix. If this rule holds, matrix multiplication operations like this one can be performed. The dot product means that we sum the products of corresponding components. So we add up the products of corresponding components. In case you're wondering, both the dot product and matrix multiplication concepts are linear algebra concepts. The important thing about matrix multiplications like this is that they represent linear functions that we can use to build up our neural network. Specifically, the weight matrix defines the linear function, and it is also called a linear map. It maps a vector space of 4 dimensions to a vector space of 3 dimensions. When we change the weight values inside the matrix, we are actually changing this function. And this is exactly what we want to do as we search for the function that our network is ultimately approximating. Let's see how to perform this same computation using PyTorch. Here we have the in features and the weight matrix, both as tensors. And we're using the tensor method called mapmul to perform the operation. The name mapmul, as we can probably guess, is short for matrix multiplication. In the next post, we'll see how to do this using the linear layer itself. But for now, we've covered the main learnable parameters of our network. A looming question is, though, how can we access all the parameters at once? There is an easy way. Let me show you. The first example, network.parameters, is the most common way, and we'll use this one to iterate over our weights when we update them during the training process. Our network inherits this parameter method from the neural network module base class, and this is where what we talked about earlier with the parameter class comes into play. It's possible for us to quickly get all of our learnable parameters like this because of the work that the module base class is doing behind the scenes. The second way is just to show us how we can see the names as well. This reveals something that we won't cover in detail. The bias is also a learnable parameter. Each layer has a bias by default. So for each layer, we have a weight tensor and a bias tensor. If you want to learn more about bias, check out the Deep Learning Fundamentals series. There's a post on DEEPLIZARD.com in that series that covers bias in detail. If you haven't already, be sure to check out the DEEPLIZARD HIVEMIND, where you can get exclusive perks and rewards. Hit the like button to support collective intelligence, and I'll see you in the next one.
People sometimes ask me if it's dangerous to make AI accessible to more people. What's dangerous is having an exclusive and homogeneous group creating technology that impacts us all. We've seen the harms being caused by companies like Facebook, Google, YouTube, Amazon, Palantir, and others. And we need people from more diverse backgrounds to try to address those harms. We need people from communities that have been disproportionately targeted with harassment to help create our technology, because they have a deeper understanding of how tech can be weaponized against the most vulnerable and of what safeguards we need to put in place. And we also need more people who are experts about people, about human behavior, human psychology, and human history. The reason I want everyone involved with AI is that you know about problems nobody else knows about, and you have skills and a background that nobody else has. I didn't know about using old cell phones to protect the rainforest, about the suicide rate for farmers in India, or about the health of goat udders. Yet these are all problems my students have worked on. I'm so glad that my students didn't believe the myth that AI is only for math prodigies, but that they knew their perspectives are valuable. We need journalists, lawyers, hospital administrators, hotel sales managers, sociologists, CEOs, historians, and more to understand the capabilities of AI. It doesn't matter if you didn't go to the right school, if math makes you anxious, if your friends and colleagues think you're the last person they'd ever expect to be working with AI. AI needs more unlikely people, and the world needs you involved with AI.